Uh-oh. Okay. All right, so what we're going to get into a little bit, what are the loads that we put on our structure, right? There's all sorts of things, dead loads and live loads and wind loads and snow loads and all these other things that are associated with it. But that's going to be covered in this class. Where are loads, where they come from, how they get applied, things of that nature, right? It's also going to deal with systems. Systems of elements, right? What do I mean by that? I mean, right, trusses, right? We're going to go into trusses. We're going to do frames, right? We're going to do stuff with computers, CPUs, right? Because that's the easiest way to handle these analysis of structures, right? Is with computers. So I'll get into this, but we're going to start with loads, and then we're going to go into the systems and how do you calculate the behavior of these systems, right? Structures 2, right, is what you'll flow into after this class, right? And this is the design of, in particular, concrete and steel. Right. So in structures 1, we're going to look at, if I have a floor in a building, what kind of load do I put on it? If I have a roof, what kind of snow load do I put on it? What kind of wind load? What kind of seismic load? That's all going to be covered in the structures 1. And then I'm going to apply those loads onto a system, right? The structure is made up of beams and columns that are all connected to each other and stuff. And so given those loads and that system, I can determine what the moments and shears and things like that are in my structural elements, right? And then once I come up with those moments and shears, I got to do something with them. And that's where structures 2 comes in. Is once you know those moments and shears, you have to design your element, right? How big of a steel beam do I need? How big does my concrete beam need to be? What kind of steel do I put in my concrete beam? Where do I put it, right? How much do I put? That all comes in structures 2. So this is where we're at, right? Is in this section right here. After you go through structures 2, these are all required for civil, right? All the way through structures 2. Everybody has to do that. Some of you are here just because in 312 right now, just because you have to. You unfortunately, if you hate structures, you're not done yet. You have to do one more. You have to do structure 2. One of the reasons for that is the FE, Fundamentals of Engineering exam. You guys heard of this before? At the end of your engineering career or engineering academic career, you have to take a thing called the Fundamental Engineering exam, right? And it is a test of all of your structural engineering curriculum. I think we have a pass rate of hovering right around 90 to 100%. So if you do well in our class, you're going to be fine. The average is usually in the 70s, 70%. We in the past have run 100% for sure. I think we have a good program. But through here, the FE exam requires that. You have to know how to do structural analysis and the design of concrete and steel structures for the FE exam at the end. So that's required as part of your curriculum. After that, though, right, I don't know how far forward you guys have looked, but there's these things in your flow chart that are called professional electives, where you get to choose like which profession, which direction you would like to study. Those things are called professional electives. If you were like, I really like, transportation engineering, right? It's lame, but you might be one of those people that like transportation engineering. There's a group of professional electives focused on transportation engineering. If you like construction engineering, right, there's actually a group of professional electives associated with construction that you could do. If the same thing with water resources, environmental, you could do these professional electives. We have a bunch of professional electives ourselves in the structural engineering realm. They are concrete 1, concrete 1, steel 1, masonry design, and timber or wood design. Those are and those are the main materials, right? Concrete, steel, masonry, and timber are like the main materials that you find structures, civil structures made out of. And so we have a design course associated with each one of those. The problem with these and you'll see as you go in, is since we only have like 3 people teaching structural engineering, we can't teach all these classes every semester, and there's not enough students in these classes to make that happen either. So we have to do these things on an every other year basis. So right now we are teaching masonry design this semester. Next spring at the same time, we'll be teaching timber and wood, right? And so we go on an alternating year. This year we taught we taught steel 1, and then next fall it'll be concrete 1. And so it depends on where you land in your curriculum. You're only going to get at most 2 of these as part of your undergraduate education, if that's the direction you want to go. That being said, if you stick around for grad school, that's a 1 to 2 year experience doing graduate school. If you do graduate school, you then would pick up the alternate year one because you're going to be around the next year, so you pick up the other material. And then also all of these other courses down here are all our structural engineering oriented classes, right? So we have a concrete. After you take concrete 1, you take concrete 2. After you do steel 1, you do steel 2. Masonry design, they don't really flow into everything, but there's this thing called structural dynamics. I teach in this class, I taught that last fall. That has to do with a structure, it actually does move, like if there's a seismic load or wind load or something like that, and there's this thing called resonance, which we saw on that Tacoma Narrows Bridge. We studied why the Tacoma Narrows Bridge did what it did, how we studied the fundamentals of the seismic code, where it came about, what are the key components to it, and where it all came from and stuff. That's the structural dynamics. This is how to model things. We're going to learn about modeling a little bit later. Like we're going to be talking about using computers. This is advanced computer use to analyze structures. That's what this guy is. And then pre-stressed concrete, I teach that one too in the fall as well, but in alternating years. These are all on alternating year schedules as well. Right. And so these are all associated with grad school. So also, it's never too early to start thinking about grad school. Right. This is the one part that I have trouble with your age group, right? And I'm like, you guys should really go into structural engineering, is that usually a structural engineer goes to grad school, right? And so then I hate to tell you that, so you're automatically going, oh my God, I'm definitely not doing it. I am sick of school. I don't want to do 1 to 2 years more of school. But unfortunately, that's just the way industry is. If you want to come out of school knowing that you get to do structural engineering, you should definitely get a master's along the way. Right, which is another, like I said, 1 to 2 years additionally. You can do these things where you reserve courses along the way and things like that, and then use them for graduate school, which speeds it up and stuff. You take them as an undergrad, but you reserve them from grad school, which kind of helps it go a little good. We had somebody just finish in a year because he reserved 9 credits of grad school while he was an undergrad. So if you find yourself ahead of schedule or behind enough in schedule that you have a little bit of free time, you can take grad courses. That applies to all schools too, right? Like if you were interested in environmental or transportation, God forsake, right? That's it. If you are interested in one of those, right, you can take grad school as an undergrad and reserve those credits and apply them and get out of here earlier in grad school. And I would say that same statement about if you want to do some part of structural engineering and civil engineering and guarantee that you get to do that when you go into work for the rest of your life, you need to go to grad school for that, right? You do. It really just enforces or reinforces your ability to do those things, right? I mean, just think about it, right? If you go through, technically you could go through your undergrad with just structures 2, and then maybe you'll pick up 1 or 2 of these, at most 2 as your undergrad, right? You could pick up, right, then think of all you'd be missing. You're missing 2 of these and all of these, right? And so if you go to get a job someplace and then the industry's like, wait a minute, like I could hire this guy or this person, right, that has this many classes, or I could hire somebody with all these other qualifications, and it makes sense. And also, that's the other thing that, it's hard for you guys to understand it too, is that this longevity of how long you're going to be doing what it is you're going to be doing, right? You're going to go, when you go to work, you're going to be working for like at least 40 years, right? And so you want to make sure that you're doing what it is that you want to do for those 40 years, right? And so doing 2 years extra at the beginning to do a little bit of grad school to focus on the subject you like the best, it's nothing in the grad scheme. Also, the real world's kind of lame, right? Guess how much time you get off for Christmas? Maybe half off of Christmas Eve and then all of Christmas Day. That's it. That's all you get, right? I remember when I was in the real world for 1 year. I graduated from Carroll College with a math and engineering applications, math with a focus on engineering, whatever. And I went in and I worked as an engineer for 1 year, and I was first of all grossly unqualified to be doing what I was doing because I had a math degree. And then I had a concentration. That's a concentration in engineering. So I had some basic classes. I think I went through about here, structures 2. That was probably equivalent to what I went through. And I didn't know what I was doing. And then I went to my supervisor. I was like, oh, like, so how much time do we get off for Christmas? And he kind of like laughed, and he's like, half of Christmas Eve and Christmas Day. And then I was just like, well, clearly you get nobody works between Christmas and New Year's. I mean, that's like no man's land. Like, you don't have to do, nobody does that. Absolutely. Unless you have paid time off, you are working that week in between. So don't be in a hurry. Do not be in a hurry to go to the real world. It's a terrible place. I was there for that 1 year, came back, never left, right? This is where I'm going to be the rest of my career. I never will go back. It's an awful place. I mean, you get paid well, right? You get vacations. There's some reasons to go. You get paid way more than I get paid if you go into real engineering. So, okay, any questions about that? Like where we sit. So this is where we're at, right? We're gonna do load systems. We'll talk a little bit more about what we're doing in this class. But I wanted to give you the overview of you may not have heard all this stuff before, right? All the classes that we offer related to structural engineering. Okay, flow of structural engineers. Let's just talk about like if you were in the real world, right? How does this, right? You may have in your mind how you think structural engineering works or how design in general works. It's probably not right? So I just wanted to let's just go through that, just so you can just set the stage for, where we fit in as structural engineers, or where structural engineers fit into the grand scheme of things. Okay, the flow of a structural engineer. So one of the first things I should say is, who do you think that we typically work for as a structural engineer? Architects. I hate architects. There's a constant battle between an architect and a structural engineer, right? An architect is like, oh, let's just make this building look beautiful and make it feel good and stuff like that, right? And then they're like, great, but you can't span 200 yards without any columns, right? And so you're like, you need to put some columns in here. I was like, well, I don't want any columns, or my client doesn't want any columns because they'll hit his door of his Mercedes on it or something, right? Like it's always there's this constant battle between the two. It's like, well, you can't have the form without the function, right? You need the structure to support what it is. And so we do. We work for architects, right? I mean, don't get me wrong. I'll talk shit about architects, but they really do things, right? Like maybe I've mentioned this before, right? You walk into Norm Asbjornsen, right? And you walk around, it's just like big open spaces and it's beautiful and you feel good. Like you feel good about being in there. And honestly, that's how I feel about this structure right now as well, right? This is nice, right? Like I feel scholarly. This is great. I feel warm and fuzzy inside because of the structure. Versus walking into Cobley Hall, and then my soul leaves my body as I walk in. It's like, fuck this, I'm out of here, right? You walk in, and you're just like, oh my God, there's no windows. And then what windows you do have, you have to look through offices to get to them, and they're little guys, they're like this big, right? And that's all there is, and there's no point of references. Architects are great in that sense, right? But I do have to admit, I'm pretty sure an architect is who came up with the eyebrows on Cobley Hall. If you look at Cobley Hall, you see all the little eyebrows above every one of the windows. So they're off sometimes, right? The original colors in Cobley Hall 2 were all orange. All doors used to be orange. That's how it was first opened up in the 70s, right? And then if you look in, if you go to one of our faculty members' offices, you'll see that the doors are scratched often, and you'll see the orange underneath. It scratches down to the base, and you see the orange door under there. And then also, all their curtains are orange because they're the original curtains from the 70s, and they match it. They're 50-year-old curtains. So that was an architect's decision as well. Sometimes they're off. Sometimes they make it beautiful. Okay. So anyways. All right, so typically what you'll do is just start out with architectural drawings, right? They meet with the client, right? The real client is the owner, right? The owner of the structure. They're the ones that meet with the client and come up with preliminary design based on client needs, right? Which it should be done, right? Like they could probably handle meeting with the client better than we can, right? Like if somebody said, hey, design a structure for me, I'd come in and this would be a rectangle, right? We're gonna do a rectangle. I mean, that's probably what happened with Cobley, right? They're gonna do rectangles. Those work really well, right? And make it a box, right? And then we'll put some rectangular windows in it, and then it doesn't turn out so great. So they're the ones that might meet with them and say, what are your needs? What do you want? And they come up with the original floor plan. So before we even get involved, there's been all sorts of stuff that's been happening between the architect and the actual client, right? And if they do it right, they get the engineer involved early, right? Just to be like, look, that's impossible to do what it is you're trying to do. Or if you do it that way, it's gonna be so expensive. And so there is as early as they can get the structural engineer involved, they do. Okay. All right, preliminary calcs from engineer to determine basics, such as building system, right? Material, right? Are we using concrete, steel, timber, stuff like that, right? Structural layout. Right, the basic structural layout. Right. Again, though, this is work as team with architect. Right. You don't just do it all yourself. I mean, and others, right? Mechanical engineers are floating around. That's the other thing with mechanical engineering that you don't hear often, too. And unfortunately, I don't think they hear about it either. A lot of times, mechanical engineers do HVAC systems, right? That's not what they're like. If I was I want to design missiles, right, and sabos and shit like that, right? Like that's what I want to go into. And then you may end up getting into that, and then doing HVAC systems in buildings, right? Because that's part of the structure as well. So there is this preliminary, because you right at the beginning they may not know, like, do they want? We'll talk about the systems later. Maybe they want a frame system, maybe they want a flat plate, maybe they want it made of concrete, maybe of steel, right? You just kind of do some preliminary calcs and you kind of come up with, like, look, based on your preliminary design, steel moment frames are going to be the one that you want, right? Or steel brace frames, or concrete brace frames, or concrete moment frames, or something like that, right? So there's this stuff that happens. Also, take this with a grain of salt. I've only been in the real world for 1 year, right? So this is based off of late 90s, me working in I talked to Tim White, who, if you pass this class and go to Structures 2 next semester, Tim White teaches Structures 2. He was a former student of mine, and he was a practicing engineer for 10 years. He still is. And so I told him, like, him and I went through this list just to make sure that I knew what was really happening in the real world, instead of me just pretending what I think happens in the real world. And so it's backed up by him. And then we have to determine loads on the structure. Right, and we're going to learn about these different loads, but there's gravity loads, right? We're seeing called dead loads, live loads. I'm just going to throw in some stuff down here, right? Live loads, self-weight, right? It's just how much gravity, right? Gravity pulls down a structure. When you think of a structural design, that's probably what you think of mostly, right? Is keeping the thing standing, right? Resisting gravity, right? And then there's also lateral loads, right? What do you think the lateral loads are? Stuff coming from the side. What do you think those are? Yeah, wind's a big one. What's the other one? Oh, look at that. You guys new to this or something? Nope. That could be. That'd be lateral loads. Yeah, if you had like a backfilling on a wall or something like that, absolutely. Oh, come on. What? No, yeah, it could be thrust. It could be thrust from a large aircraft or a large aircraft hitting it. Like, again, it took me a second. Yeah, large aircraft can hit it. Yes, that is true. That is true. Right? I mean, allegedly, right? Like, we don't know if it really happened, right? I saw on YouTube, watch some YouTube, there's a lot of conspiracy theories that 9/11 didn't happen. I'm not, okay, it did happen. It did, okay? I'm just saying some people think that it didn't. Oh, come on. Come on, I'm not moving on until someone says this other lateral load, a side load on a structure. It's getting awkward. I'm gonna start calling on people. CJ, you got a guess?
Earthquake.
Yes, that's it. It's an earthquake load, which is weird, right? It's weird to think about that being a side load. Because what it is, right, is the ground is shaking underneath it, right? It's going, and it does go up and down some, but it doesn't go up and down as much as it goes side to side. So that's the difference between a S wave and a P wave, right? So we're talking P waves. P waves cause, right? You learned about this. Did you learn about this? S waves. S waves are this. P waves are like pressure waves going back and forth. And so that's where the structure, the base goes on. And then imagine what that would do to the structure, right? If it wants to stay still and this is moving underneath it, it's like pushing it from the side. It's not pushing it from the side, but it's like it, right? And actually how we analyze it is we determine how much the shaking underneath causes like, displacements on it, and then we come up with an equivalent lateral load that would give you the same displacements that would happen if the ground was shaking. So that you're forgiven in some sense because it's not like wind's really easy, right? Because wind's, you can envision it. Wind pushes on it like a big sail, and then it catches it, and it has to resist it. Like I get, you get that. But the seismic is a little weird. So the other one is earthquakes, right? Which we have, when we design for seismic loads, we have a lot of seismic loads in Montana, right? The old code used to have us in the same category, basically, as California, right? Why do we have such big, large seismic loads in Montana? Yellowstone, right? Especially us. And by all, it's not all Montana that has high seismic loads, but us and Bozeman have huge seismic loads because of Yellowstone, right? Because of all the seismic activity that takes off down there, right? And super volcanoes, right? Super volcanoes. But yes, aircraft hitting the side of your structure is also. But to be honest, they don't design for that, right? They design for wind and hurricanes. I think that's what controls designs on the East Coast is the hurricane loads, right? And then usually it's okay to handle aircraft loads, but the fuel is what the problem was, right? And the explosions and stuff like that. I still think it's bullshit that you guys weren't even alive during that time, except for Justin, right? Do you remember any of this as Justin? Probably not, right? Yeah, one or two. Honestly, it was a very scary time. That's when I moved to Seattle. I refused to go to any baseball games and stuff like that. There's a large concentration of people because I was from Helena, Montana, and I was like, I'm not fine. And then I went to Seattle, and I'm like, that's where I did my grad school, University of Washington. And I went to Seattle, and I'm just like, oh my god, look at all these people. This is scary. And then I moved there in October of 2001, so it was just within a month of when that happened. I was terrified at all times. Oh my god, they're gonna kill everybody at the Seahawks game, and I didn't go to Seahawks games and stuff. It was a freaky time at the time. Talk to your parents about it if they were alive at that time. It's getting to the point. I could be all of your guys' parent, and I don't like to think about that because it makes me feel old. I'm just one of you guys. All right, so you got to determine the loads, right? Once you come up with those loads, then you put it on the structure, right? Oh yeah, I would have got determine loads on. Put a space here. Load effects, maybe load effects. Right? This is the structural analysis. Oh, I'm gonna. Right. Structural analysis. Right? There's this thing called load paths. We're gonna trace loads, right? If your load goes from one thing, it always has to make it to the ground. Your load always has to make it to the ground. So there's this idea of load paths, where it starts and where it ends up, and how you go from one to the other. That's load paths. But just generally speaking, though, just the structural analysis, right? And oftentimes, what it's going to be nowadays is you're going to put it into a computer, right? You're going to say, you're going to draw your little structure and apply a load, and then you're going to run it, and it'll tell you, what are your moments and your shears and your axial loads and all your elements, and things of that nature, right? Oh, we're going to have this idea of gravity loads versus, right, we already talked about that, but those have to be applied. You have two different systems for these. Right, you have a gravity system and a lateral system, right? You have to design both of those things. But so you determine those loads, then you take those loads, you put it on your structure, you do an analysis, and out of this, like I said, comes right? Moments, shears, axial loads, and all elements. Right. And this is where we're at. This class is going to be right there, those two things. Determine loads in the structure, the gravity loads, and then the effect that those loads have on the overall structure. Right? This is structures 2 is going to be E, which is design structural elements to satisfy requirements, the demand. we'll start doing some calcs at some point. Right now, though, it's just going to be keep you engaged. I'm going to make you write this stuff out. I'm going to type it super fast. I'm a pretty quick typer. I took typing in high school. Anybody say typing in high school? See, I don't think they teach you that much. Do you have to look at your fingers when you type? You do, don't you? You losers. You can say you don't, but you do, right? You should have a typing contest sometimes. See how quick we are. Anybody else, who took typing in high school? Yeah, damn right. I mean, yeah. I don't know how needed the skill is anymore because you can just talk to it and write it down. It'll write it all for you. Dictate it, and then it writes it really quick. All right, what are those requirements? Strength and stiffness. All right, you have to make sure that our elements are strong enough and stiff enough, right? So they don't deflect as much. That's what the stiffness is. You have to determine that. That's one of the requirements. They have to be stable, right? Stability, right? Things become, even if they're strong enough and stiff enough, they may be unstable, right? They may this thing called buckling, right? Did you learn about Euler buckling back in the day? It's strong enough, but there's this built-in instability that can happen where the things get up to sort of, and they pop out and then they collapse based off of that. And so that's they have to be stable as well. They also have to be serviceable. This thing called serviceability. That's not how you spell it. Serviceability. Which is crazy when like the ability words, right? Because sometimes it's IBI ability, like constructability, but then you can also spell it constructability, but then you're just taking two words and they're making it one word, right? Serviceability, but then sometimes it turns that happens, it turns into an I. You'll see. As you grow older, you'll see this, and it'll drive you crazy as well. But the good news is you don't need to know that anymore because computers know that and they're correct as you move along. But serviceability, what do we mean by serviceability? It just means even if something's strong enough and stiff enough and stable, doesn't mean it's still going to be a good structure or not, right? An old professor of mine used to say that he could design a strong enough, stiff enough, and stable enough structure out of cables and 2x4s. Right? You could do it, right? You have 2x4s and all these cables strewn about, and then you could make a floor by putting, 2x4s across those cables, and like it would work, right? But it would not be usable, right? Because it'd be like you walk around and it's like moving and being flexible as you're walking around, stuff like that. It's not going to work, right? It's not going to work for it. Or you make it and all the windows leak, right? Or there's too much deflections in the floor. I guess one of the big. I have a friend of mine from grad school that his job, we're almost out of time. I talk way too much on stuff. Is it Melena's fault for showing us the videos earlier? And he does structural forensics, right? He comes in and looks at failed structures. And I think, oh, that's great. Like what a sexy job, right? Where you're gonna go look and see why those buildings failed, right? But most of the time, the failure is, the floor deflected too much. And there's one hospital they showed me once where all the floors were like concave, like down in the middle. So all their equipment and patients and stuff would roll to the middle of the thing. And so that is a failure. And that kind of failure is serviceability. It is not a structural failure in terms of strength and stiffness. It is, so it's not usable, right? It's not usable afterwards, right? You got 2 minutes left, you little... Not usable, right? Let me finish this one. EF, iteration, right? Once you come up with those designs, there's lots of iterations. Maybe you go through it and you're like, oh my God, we got to the end here. Oh, I left out one. Economy. That's the other one. Right? You get to the end, you're like, oh my God, this is going to cost way too much money. It's not economical. So that's one of the design considerations. So if you get down there like, oh my God, this is going to cost too much money, boom, come back up, all the way back to here and change what your system is. Oh, steel's too expensive. Or sometimes between here and here, steel costs go way up and it's too expensive by the time you get to the end. So you have to switch to a concrete one. They have to come back and do this whole aspect again. So that's iterations. You gotta go back and forth. And the last one is construction administration. We'll get into that last. We'll do that. That's where we'll take off on when. I'll give 30 seconds off. Okay, so yeah, we'll go back here to construction administration, and that's our last step. It's like you actually are involved in the construction of the structure, which is pretty cool. That's what honestly drew me towards structural engineering, was this idea of like being part of making stuff, right? That's gonna sit there for your whole life. All right, break. See you guys on Wednesday. At some point, I'm gonna get a homework together. I don't know what's gonna be on, but it's gonna be great. It's gonna be great. Yeah, honestly, Sean.